This is what our weighted combination, and each it just take a set of vectors and a scalar weight. So here it is the scalar weight lambda 1 and vector v1, lambda 2 and vector v2, scalar lambda 3 and vector v3. So till it just goes with lambda n and vn. So where we can just shortly specify as like summation of I, which is equal to 1 to n and lambda I vi. So this is what exactly, yes dear friends, set of vectors multiplies each by a scalar weight and sums the result. NP dot this linear algebra, so solving this system, yes, would fail, and here no unique coordinate would exist. And dear friends, when coming towards this data science interpretation, yes, this operation is what exactly this PCA, that is PCA projection, that is projecting data into new bases. So dimensionality reduction, that is what happening. And not only here, yes, SVD transformation, that is for coordinate change, and feature transformation for new representation, that is what happening, dears. We didn't use a list here to create a vector because lists are slower for heavy maths and mathematical operations become awkward. Kindly just observe, dear friends, here we have just discussed about spans and the same thing about linear independent. Yes, okay. So here, what is this independent? Of course, no vector is redundant. That is what independent. And to the same spanning, yes, that can reach any point in the space. You would just ask when to use this Pearson or when to use this cosine similarities. So for them, kindly just have a note, Pearson correlations when you care about relative changes. One thing kindly just observe, dear friends, if we are having a rank that is less than number of vectors, so it is a dependent, and if it is a rank that is equal to number of vector, that is independent. Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, we bridge foundational linear algebra concepts with their direct applications in data science and generative AI. Yes, we are just going to begin with this vector set. Yes, and then we just move on to this linear combination. Yes, the fundamental mechanism for constructing vectors, and we move on to this independence, which ensures that our representation are free from redundancy. From there, we explore the concept of span. So which defines the space of all possible combination, and yes, the basis. Yes, dear friends, the minimal and most efficient representation of that space. Building on this foundation, we transition into practical similarities, that is Pearson correlations and cosine similarities. Dear friends, which are essential tool for understanding patterns, relationship and structure in high dimensional data used in modern AI system. So let's just start with the necessary libraries. Yes, dear friends, kindly just observe. Here we have just imported our necessary libraries. The first one, it is all about the NumPy. So NumPy library and assigning it with the alias name NP. So NumPy provides efficient numerical array operation and is foundational for a linear algebra component. Next, we have just included matplotlib. Yes, this imports the plotting module pyplot, and it has an alias name as PLT, and it is used for creating visualizations such as graphs and figures. Next, we have just imported npl underscore toolkits, that is mplots 3D. Difference, this imports the Access 3D toolkit, which enables 3D plotting capabilities within matplotlib. Next, we have just included warnings. Dear friends, this import Python's built-in warning models, which allows control over warning message generated during execution, and this suppresses all warning message. So it ensures a cleaner output by preventing non-critical warnings from being displayed. And dear friends, of course, you all know about this one, matplotlib inline. Yes, this is a new Jupyter Notebook magic command. It ensures that all plots generated by matplotlib are displayed inline or within the notebook rather than in a separate window. And here I have just given an exact code. Yes, this line begins updating matplotlib runtime configuration parameter using a dictionary. And here this exact dictionary has an key and pair components as like a default size of a figure to 7-inch and 5-inch tall, 7-inch wide and 5-inch tall. And yes, this enables the grid lines on all plots by default, and this sets the transparency of the grid lines to 30%, so making them subtle and less visually dominant. And next we have set the default font size for all text in the plots to 12 size, 12 points. Okay, and dear friends, next we have the print functionalities. Yes, the prints the install version of NumPy by accessing the version attribute. And yes, the next line, it just shows the print confirmation message indicating that the environment setup has been finished successfully. Let I just execute, and kindly just observe. Yes, the setup is complete, and the NumPy version here, it is 2.3.5. Yes, dear friends, the environment is ready. Now let me just move on to the vector set. Dear friends, vector set, it is a simple collection of vector. So here, if I just specify, this is the exact vector set, and it has a collection of vectors as like v1, v2, v3 till vn. Yes, this is all the vector collections. And think of it as putting a vector into a bag. That is what vector set. And this set can be a finite, or this can be an infinite also. Yes, if it is an infinite, it is a subspace. And even this vector set can be an empty difference which arises in matrix null spaces. In Python, we typically represent a finite vector set as a list of arrays or as a columns or rows of a matrix. Yes, let me just create a set of vectors here, and we just have a discussion here. So we are just going to have 3 vectors with four-dimensional spaces. Four-dimensional spaces, that is was r to the power of 4. Okay. So here we have v1, v2, v3 as our vectors, and kindly just observe this vector. Each we are just having with 4 components, and it is created by using this NumPy array. Each element corresponds to one dimensional. And dear friends, kindly just observe this one we have just used array for the creation, because arrays are designed for mathematics, and mainly it is used for fast calculation, easy vector operation, works well with matrices and linear algebra. We didn't use a list here to create a vector, because lists are slower for heavy maths and mathematical operations become awkward. But once on creating the vector, we are just storing it in a list. Why list here? Yes, because lists are convenient for looping through vectors. So storing collections or flexible organization. So that is what here we used to make it in combinations of 3 vectors. Yes, it creates exact list that containing 3 vectors, and this is the one way to represent a vector set programmatically. Okay, kindly just observe here we have used the function enumerate, because numbering starts from 1 instead of 0, making the output friendlier for the user. So who continues to resist zero-based indexing despite a decade of exposure. Okay, and yes, we have used this for loop. Yes, of course, to enumerate starts indexing at 1 instead of 0. And here this I, it is for index, and here this V, it is for vector itself. And here we are just printing each vector in formatted form, labeling them as like V1, V2, V3, like, okay. And dear friends, kindly just observe here we have used a column stack. Yes, this stacks the vector column wise into a single matrix. Each column corresponds to one vector, and this results in, of course, we just have 4 into 3 matrix. And kindly just observe, dear friends, that can be printed here by using these matrices. Okay, so matrix representation, and next it just shows the shape of this matrix, and with the shape 1. So this is 4 rows, and this shape 1, it just gives the number of columns as 3 columns. Let me just execute it and view the output. Kindly just observe, dear friends. So here we are having, yes, we stored 4-dimensional values in the vectors. That is 4 vectors in a vector set V1, V2, and V3. So totally we have 3 vectors, and kindly just observe how this happens in a programmatical manner. It is yes, here we go with this is our matrix, and here we have V1, V2, and V3 as our result. Okay, and when on just storing, yes, it just made it into the 4 into 3 matrices. That is 4 rows with 3 columns, where each column is a vector. Difference, the matrix representation is far more common in practice, because it enables efficient linear algebra by using np dot lean algebra. Okay, that is, this is what the exact routine. But here what we have just utilized is, kindly just observe, in linear algebra here we have used this matrix formation. Yes, it is very much easier for linear algebra operations or solving systems, and checking independence, transformation. And here we have used column wise, because instead of row we have used a column, in because of in linear algebra vectors are commonly treated as column vector. Many formula and matrix operations expect this format. But using rows also is possible, but often lead to confusion when we just make use of transpose. Okay, so here we have just used column wise, and yes, it returned the print statement of the shape. Yes, kindly just observe, it is 4 row 3 columns. Okay, so 4 row 3 columns, where 4 dimensional vectors, and with 3 of them, that is what the exact thing we have resulted. Okay, let me just move on to linear weighted combination. Difference, linear weighted combination, also called a linear combination or linear mixture. So it takes a set of vector, multiplies each by a scalar weight, and sums the result. So how it seems to be is, yes, this is what our weighted combination, and each it just take a set of vectors and a scalar weight. So here it is the scalar weight lambda 1 and vector v1, lambda 2 and vector v2, scalar lambda 3 and vector v3. So till it just goes with lambda n and vn. So where we can just shortly specify as like summation of I, which is equal to 1 to n, and lambda I vi. So this is what exactly, yes, dear friends, set of vectors multiplies each by a scalar weight and sums the result. And dear friends, here this exact lambda I, which I just specified, yes, are real valued scalar. Sometimes also we call this as weights or coefficient. And here all vectors must share the same dimensional. Kindly be aware about that. Okay. So this respectively simple operations in a single most important building block in linear algebra. And dear friends, indirectly underpins regressions or PCA, neural network, and almost every other technique in applied linear algebra. Okay, so let me just move on to the code here. So kindly just observe, dear friends, these are the exact scalar. So lambda 1, lambda 2, lambda 3. And yes, we have three vectors as like v1, v2, v3. Yes, with the combination here, we just get lambda 1 into v1, lambda 2 into v2, and lambda 3 into v3. And dear friends, in example, we have just specified as like lambda 1, 2, 3, which it just has lambda 1 as 1, lambda 2 as 2, and lambda 3 as minus 3. Okay, so this is what the exact vector contributes to the final result. Let me just discuss how this happens. Okay, and next kindly just observe these one all it's just going to print. Okay, the print the first coefficient or second pair and the third pair. Okay, and making this exact line, it just prints the full linear combination expression along with the computed result vector. Okay, so where we just get w is equal to lambda 1 v1, lambda 2 v2, and lambda 3 v3, and we resulted it with w, and that exact resulted is which is what the summation of. Okay, yes, let me just have it step by step. So kindly just to see here, here we are having that exact combination as like so once on all making this exact each and every separate values. So this is what lambda 1 v1, lambda 2 v2, lambda 3 v3, and then we are just summing up. And dear friends, kindly just observe the linear weighted combination produces here a resultant. Let I just execute, and yes, this is what the resultant. Both wherever we just specify by using direct functionality or step-by-step functionality, we just getting the exact value. And let me just see how this mathematically happens, because let I want to visualize it how this is happening. So kindly just observe w, which is equal to, that is what the main weight, and lambda 1 and to the vector 1, yes, 4, 5 and 1, and summation with lambda 2 with the vector 2, so minus 4, 0, minus 4, and the last one, it is a summation of, this is the scalar, third scalar, and it is multiplied by with the third vector, it is 1, 3 and 2. So let me just see the resultant. Kindly just see when we just make it towards step by step. Yes, we just resulted with 4, 5 and 1, and for the second one it is minus 8, 0, minus 8, and kindly just observe this one, it is minus 3. So what would be the resultant? Yes, of course, kindly just observe it is minus 3, minus 9 and minus 6. And yes, once for all, the exact result. Kindly just to see here, dear friends. 4, this one 4 minus 8 minus 3. So the resultant, it would be minus 7. 5, 0 and minus 9. So result would be minus 4. 1 minus 8 minus 6. So the exact result, it would be minus 13. So this is what the output. And dear friends, once more, I just let you know. So this is the exact scaled vector together to produce the final result. And yes, this one exactly mainly used in the foundation of linear regression, that is weighted sum of future, and it is also the foundation of PCA. Yeah, there is also weighted summation of basic vectors, and of course it is also mainly used for neural network, where we just make use of z is equal to wx plus b. So this is also here we just include the weight. So, dear friends, this is very much important linear combinations, which are very much being a foundation of spans or vector spaces or machine learning, graphics, physics, and neural network. And in essence, complex directions can be created from simpler ones. Now, let me just move on to have something in a geometric manner. Yes, dear friends, we are just going to have a geometric interpretations. So that exact visualization would just, here I have a code that demonstrate one of the linear algebra's most remarkable phenomenon. Yes, two independent vectors can generate an entire plane. And kindly just observe, dear friends, here we have a combination. There's V1, V2, yes, two vectors we have, and to the same we also have an array functionalities. And kindly just observe, here we have a subplot 1 comma 2, yes, one row, two columns, and we are just going to have a control of figure size with 12 into 5. Okay, so kindly just observe because this controls over the size of the figures to in arrays containing that we are having two plotting areas. Okay, and I just want to have it as like an panel A and panel B. Okay, so left side panel A and right side panel B. Okay, now let me just move on to the coding in depth. Kindly just observe, dear friends, here we are having the vector V1. Okay, so it defines the first vector V1 with a two-dimensional component, and here V2, that is also with a two-dimensional component we are having. So these two vectors will be used to generate line combination. And here we are having the panel A, kindly just observe, and this exact functionality, it just to say axis 0. Axis 0, it is what? The subplot left side that it specified. Okay, so let's subplot for drawing and observe this exact code. So it defines a list of specific coefficient pair for this lambda 1 and lambda 2, that is each with a color. So here we have weight, we have weight for V1, that is vector 1, weight for V2, and color for visualization. That is what. So this is for the V1, this is for V2, and here this is what the combination. And we have a loop with each combination of the functionalities. Okay, what that specifies is here we have A, B, C. Yes, of course. It just takes the weight of vector V1, and B, it just takes the vector V2, weight of vector V2, and the C, yes, it is for the color. And when on computing this particular function, observe W is equal to A multiplies V1 plus B multiplies V2. So once done, yes, we are just going to draw an arrow from the origin 0 comma 0, okay, and to pointing it as like W. And dear friends, kindly just observe this exact code. It just specify the arrow style. Okay, and kindly just to see here we have an arrowhead and the exact color, what is just to specify using this color as like assign, and here the line thickness, it is specified as like 2. And dear, labels each rows with its coefficient, and coefficient as like a comma b. Okay, so that is what here it is specified, of course slightly offset from the tip. Okay, now let me just have the axis formatting, and it just specifies that the visible coordination range, and next it just ensure the equal scaling on both axes, that is no distortions. Okay, and next let it just draw an horizontal and vertical axis, and next it is just going to specify, yes, it is a set title A, that is panel A, and here we just have the label axis. So yes, dears, now let me just move on to the panel B. Kindly just observe, here it is axis 1, so it is the right subplot, And next we have an line space. Kindly just observe, it just generates 15 evenly spaced value between -2 to 2. Okay, so -2 to +2. Okay, so these are the possible weights, and we have an initialized an empty list, okay, to store that result. And next, we started with a loop, that is a nested loop, overall combination of A and B. This creates a grid of weight. And when on combining towards this, kindly just observe, dear friends, we have already specified W is equal to A into V1 plus B into V2. That is, compute the linear combination of each pair. And next, we are going to store each resulting vector, okay, and converting that list into NumPy array for easier plotting. And here we have used the scatter because this, it just shows many generated points, all reachable combinations. So the cloud of dots visually reveals the span. But we are not making arrows for all the points because far too cluttered, because if we just make all the points as like an arrows, it seems to be cluttered and the plot would resemble panicked spaghetti. So that is what we didn't use it. And yes, here we are just going to have our data. Kindly just observe. So this one draws the vector v1, and this one, yes, it just plots the vector v2. Okay, and let me just have the label 1 and label 2. So this one for labels for vector v1 and this vector v2, that is what here it is specified. It is the same, similar to the one previous, as to have limits, equal scaling, axis lines, and towards the labels. And dear friends, kindly just observe, here we have just made it as a tight layer to make adjust spacings to avoid overlapping. And yes, if you want, you can just save the figure as like an image file, and let me just have the execution and observe it. So here we just got the output. Kindly just observe, dear friends. And yes, this panel A, it just shows 5 specific combination of V1. So here we have, that is as like 1 comma 0, 0 comma 1, 1 comma 1, 1.5 comma minus 0.5, and minus 1 comma 2. So kindly just observe here. So this is how the each and every values we have just specified. This is 1 comma 0, this is 0 comma 1, 1 comma 1, 1 comma 1.5 comma minus 0.5, and last it is minus 1 comma 2. And let me just have, this is as our panel B. Okay, it just samples, we just have totally we are having -2 to +2, that is -2 to +2. So totally we have having 15 samples, okay, on a grid, and plots all resulting vectors. And even with this limited range, the point fills a region of R2. Kindly just observe. And we extend the range to -infinity to infinity. Yes, every point in the plane would be reachable. So this is the essence of span. That is, two linear independent vector in R2 can reach any point in R2. So yes, dear friends, here linear weighted combination or the mechanism that create subspace. So the specific weight lambda I will select one point in the subspace. So the totally of all possible weight defines the entire subspace. So let me just move on to the linear independence. Dear friends, a set of vectors is linearly dependent if at least one vector can be expressed as a linear weighted combination of the other. And the set of linearly independent if no such combination exists. So think of in this way. So each independent vector carries genuinely new information that the other vector do not. And here a dependent vector is redundant. It is already reachable for the others. Let me just discuss it with this example. So kindly just observe, dear friends. So here we have a vector. So let me just discuss on towards vector V. And this defines the vector set with two vectors in R2. So two vectors in R2, that is vector V1 and V2. That is what, and here this V is a vector set. Okay, and let me just have a view of that printing. Okay, so next it just shows a for loop. So yes, this loop through the vector, so with I as an indices starting at 1 and V with a vector. Okay, it just prints each vectors in the form of V1 comma V2 and it just goes on. Okay, so yes, here let me just have this exact value. Kindly just observe, this is a ratio check, okay, which it just computes element wise ratio. So element wise ratio, how it just happens is, kindly just observe here. So V1 of 0, V2 of 0, V1 of 1, V2 of 1, so like that. Okay, and that it just prints here, kindly just observe, prints both ratios with the formatting. And lastly, it just have a conclusion whether this is equal or not equal, and therefore if it is not equal, okay, so therefore no scalar that satisfies this function, and the set is linearly independent. And here we have one more example that's discuss about the dependent. Okay, so here we have the same one, the set, vector set, and here it just named as like set yes. And with this for loop, we are just going to have the printing of the vectors. And once for all, let me just have the vectors, that is compute element wise. Okay, so element wise vectors that has to be displayed, and let it just displays both the ratios also, and within the ratios it just shows that as ratios are equal and with the same scaling factors. So yes, kindly just to see here what it is specifying is yes, S2 which is equal to twice S1. Okay, let me just discuss how it happens. Okay, so yes, the linearly dependent. So the set which is provided here is linearly dependent. That is what it is given. So anyhow, let me execute and observe. So dear friends, for this two vector, we have V1 and V2. We have the two-dimensional, and the independence check is straightforward. Yes, if one vector in a scalar multiplies of the other, the set is dependent. Okay, and in the set V, kindly just observe the element wise ratio or 1 by 2. So 1 by 2, so we just get 0.5. And here we just specify 3 by 7, which is equivalent to 0.4286. So they differ, they are not equal, so they differ. So no single lambda satisfies this particular V, that is this vector. Okay, so that is what the set is independent. Now next, let kindly just observe the set yes here. Both the ratios are 0.5 and 0.5 equivalently. But here one thing it is there, kindly just observe dear friends. Here we have S1 which is 1 comma 3. S2 it is 2 comma 6. Kindly just observe this S1, if I just multiply with twice, okay, we just get the resultant of S2. So here S2 which is equal to 2S1. Okay, so that is what it is specified. So with this combination, the set is dependent. One vector is completely redundant. That is what. Okay, and dear friends, this independent vectors point in genuinely different direction. they are not collinear. So dependent vectors are collinear. So they lie on the same line through the origin. Let we discuss one more with a hardener example. Kindly just observe, dear friends. This one we have four, okay, four dimensional with four vectors, where independence is impossible to determine by the visual inspection. The systematic approach uses matrix rank. Okay, so but we can preview it here. Okay, let me just observe how the exact output comes here. Now, let me just stack all four vector as a column of matrix. Okay, so column of a matrix. So here T, which is equal to, so we are just differentiating with the uppercase. Okay, so here kindly just observe, we would just specify as like a T resembles of R 4 into 4. Yes, this is the standard way to analyze independence computationally. Okay, so now let me just print, of course, here kindly just observe the print the matrix so we can inspect it structure, and here we have the number of rows and number of columns. Of course, both are 4 only. Okay, now let me just move on towards here. Kindly just observe LINALG. So previously I have just specified it is what the linear algebra functionality. Okay, it just computes the rank of a matrix. And here rank, it just specify, yes, number of linearly independent column. And once done, yes, it is just going to print the computed rank, and it's just going to print the number of vectors also. That is mainly, kindly just think it is all of column wise. Okay, and next, dear friends, here we are just going to have our left side computation. Okay, so left side computation as like T1 plus T2 plus T3, where it just gives the resultant towards twice T4. Okay, so this provides a specified dependency relationship. Let me discuss how this is happening. Okay, and kindly just observe here, we are just going to have it as this is what our left hand side, and this is what our right hand side. And let me just check whether it is both or equal or not. And one thing observe, if it is equal, okay, the dependency is confirmed. And let me just execute and observe here. Yes. Okay, so kindly just observe, dear friends. So this is what our output. So first of all, it form a matrix from the vectors, and next it just compute the rank and compare it with the number of vectors. And here one thing kindly just observe, dear friends, if we are having a rank that is less than number of vectors, so it is a dependent, and if it is a rank that is equal to number of vector, that is independent. And here what we are just having with this dependency equation, kindly just observe, dear friends, here on left hand side T1 plus T2 plus T3, which is equivalent to, we are having that is twice T4. Okay, so you can also rewrite it as like T1 plus T2 plus T3 plus minus of 2T4, which is equal to 0. Yes, this is exactly the form of the formal definition of linear dependency. Okay, a non-trivial combination equals to this zero vector. So even though, kindly just observe, dear friends, even though we are having four vectors, that is T1, T2, T3, T4, they only span a three-dimensional space. Okay, so one vector, yes, it can be built from the other. That is what. And dear friends, this has an amazing functionality, that is rank defense deficiency or redundant features. Yes, it is very much used in data science. Okay, so data science connections that leads to unstable regression or multicollinearity, or even though need to discuss on PCA and SVD further sessions also. Okay, now let me just move on to a formal definition of linear dependence. Dear friends, here kindly just observe one main important thing. See, we are having a set. Let our set here be V1, V2, V3 until Vn. Okay, is a linearly dependent if there exists a lambda 1, that is a scalar lambda 1 till lambda n. If not all 0, so such that lambda 1 V1 plus lambda 2 V2 plus lambda 3 V3 till it just goes plus lambda n Vn, which is equal to 0. So the set is linearly dependent if only solution is trivial one. So trivial one, which is what it is? Yes, of course. Kindly just observe anything else like a lambda 1 which is equal to lambda 2 till which is equal to lambda n equals 0. Why? Why the set equal to 0? Because setting the equation to 0, that is rather than isolating one vector on the left. So emphasize that independence is a property of an entire set, not of all individual vector. No vector holds a privileged dependent position. Okay, so here we just discuss about this special case, the zero vector. That is, any set containing 0 is automatically dependent. Because here, kindly just observe one thing, dear friends. Of course, let I have like this. So lambda 0 into 0 plus 0 into V1, if which is equal to 0 for any lambda 0 which is not equal to 0. Dear friends, this exact demonstrate that as any set containing a 0 vector is dependent. So let me just discuss it by using this code. Kindly just observe. So here we have, kindly just observe this Z that creates a 0 vector with 3 components. So yes, here we have Z which is equal to 0 comma 0 comma 0. Okay, and next let me just define another non-zero vector, that is 1 comma 2 comma 3. And dear friends, kindly just observe here this one we are just defining, that is you can multiply the 0 vector. Okay, so you can multiply the 0 vector by any non-zero scalar. So the result is still the 0 vector. Okay, so now let me just choose a non-zero scalar. Okay, a non-zero scalar, that is lambda 0 which is equal to 42. Now what happens? What happens the resultant? Yes, kindly just observe here this lambda 0 into Z plus 0 into V. So what we are just going to do, observe dear friends, this one, this is what the computes the linear combination, that is 42 into 0 plus 0 into V, which is equal to 0. So now let me just print this 0 vector, and next let me just have the second vector also, and let me just display the computed combinations also, and let me just check whether the result equals to 0 vector or not, and then we confirms that at least one combination, that is one coefficient, is a non-zero. And last but not least, let me just discuss about the final conclusion, that is the set is whether linearly dependent or not. So yes, here we just go. So this is what the output. So kindly just observe, this is what the 0 vector. Okay, and next we have our vector 1 comma 2 comma 3, and when we just make use of this linear combination, what we just get? Yes, we just get that this exact one, whether it is equal to 0. No, it is not. So yes, we have that lambda 0 which is equal to 42. And lastly, the zero vector always satisfy its conditional trivially. Yes, so any set containing the zero vector is automatically dependent. And dear friends, here we are making use of this zero vector because this zero vector contributes no direction, no magnitude, no information. And yes, this one, it is very much important for a data science interpretation, because if a data set contains a column of all zeros, then it is linearly dependent. It reduces the matrix rank. It can break algorithm like ordinary least square or matrix inversion. So yes, think of independence as like each vector must add something raw, and the zero vector adds nothing. So it immediately violates independence. Okay, dear friends, and here I just want to have make a combination of explanation. Kindly just observe here. If we have anything as like a linear combination, yes, that builds the vectors. Okay, and yes, if we have anything as like combinations of connections of independency, yet kindly just check with the redundancy. And yes, with this zero vector, automatically it just makes the failure of the case. So now let me just have a visualization of independence and dependence. Okay. So yes, here, dear friends, kindly just have a view of this. So here on visualizing this, okay, so yes, kindly just observe here we are making use of subplot, and yes, this creates a figure with two panels. One is for left one, yes, it is for independent set, and right for it is as like an dependent set. Okay, now let me just select the left subplot for this independence vector. Okay, and dear friends, here we have two vectors of two-dimensional as two vectors. So vector v1 with 1 comma 3 and vector 2 with 2 comma 7. So these vectors are not scalar multiplies, so they are independent. Okay, and here this exact annotation, yes, it draws the vector v1 as an arrow from the origin. Okay, and here this one, yes, this is also, of course, this exact plots the vector v2. And dear friends, kindly just observe we have two labels for vector v1 and vector v2, and here we have a loop functionalities where this loop, it just loops over a nested loop. Okay, so it just loops over each vector, and of course also many scalar values. Okay, and that exact many scalar values, it just spans from -3 to 3, and how many? Of course we have 100 number of values. Okay, amazing na? So yes, and that generates scaled version of each vector. That is what the main thing important. And kindly observe, dear friends, we are just going to plot as many points along each direction. So visually forms lines through the horizon. Okay, and next here it is standard formatting for equal scaling of visible axis. Okay, and let we just have our title that emphasize vector point in different direction. Okay, and yes, dear friends, here let me just move on to this panel B. And yes, amazingly, we have just switches to the right subplot, and it just defines the two vectors here, S1, S2, and of course, I think we have already discussed about this 1 comma 3 and 2 comma 6. Here, what it just remembers, yes, of course, yes, most of them are right. S2, which is equal to twice S1. Okay, yes, these are linearly dependent. And here we just have the annotation of the same thing. Okay, so it draws both the vectors, and next it is having the labels of each vectors. And dear friends, observe here this exact line. It just generates point along multiples of S1. Okay, multiples of S1. So this produce a single line through the horizon. And next we just move off with this title. Okay, so here kindly just observe this title highlights vector lies on the same line. Okay, now of course you all already have seen about this. I just want to adjust the layout, and let me just save this figure, and let me display it. So here we have the output. So here kindly just observe, dear friends, this panel A shows two independent vectors that point in different direction, but together they can reach any point in R2. They span the full plane. And here this plane B, panel B just shows a dependent pair, that is S1, okay, and here S2, that is S2, it is twice of S1. So both vectors lines on the same line through the horizon. Adding the second vector, it just contributes 0. Now reach the span remains a single line. Difference independence means each vector adds a new dimension to the space. But dependence means at least one vector is already covered by the other. And yes, in data science terms, a dependent feature is a redundant feature. It provides no information beyond what the other features already encode. Okay, now let me just move on to the subspace and span. Difference, a subspace is the infinite set of all possible linear weighted combination of a set of vector. So the process of generating this set is called spanning, and the result is the span of the vector set. And dear friends, one thing I just want to let you know. So here, if you just think about the span as a verb, vector span is a subspace. Kindly just think about a subspace as a noun. The result would be spanning. So formally, a vector subspace must be closed under addition and scalar multiplication, and must include an origin. Kindly just observe. So this means take any two vector in the subspace, add them or scale them, and the result is still in the subspace. So setting all weights to 0 gives 0, that is confirming the origin is included. Now let me just discuss with the coding. So observe, dear friends, here we have, yes, subplots is that. Okay, so create here, even though we just specify subplots, of course, here it just creates a single plot figure. Okay, and this exact figure, it is with the figure size, and the axis, it is the plotting area, and of course the size it's set to 7,5. Okay, and dear friends, here we defines the vector. Kindly just observe, it is a two-dimensional value. Now let me just create the span of one vector, which is all scalar multiples of the vector. Okay, so here kindly just observe, this one generate 500 scalar values between -3 to 3. So that is what given by using this linear space. So combining this, we would just get, observe it. So we would get lambda v for as many as lambdas. So as many as lambdas is as many as 500, that is okay. So now this one multiplies each scalar. Kindly see this one, np dot outer, it just multiplies each scalar with a vector. So here it results this 500 points in a 2D functionality. That is what we are just going to see here. And yes, we have an functionality, that is plotting functionality. So this one would just plots the resulting points, that is forming a line through the horizon, and it is going to be a dashed line, and it just represents it with a subspace. Okay, so that is what. And next we have an original vectors that draws the vector v as an arrow. Okay, and next it just labels the vector. And kindly just observe, dear friends, here we just show the specific scaled value. That is what here, specific scalar value. So that loops over selected scalar values, maybe as like negatives is there, fractional points also there, and of course positive would also there. And yes, here it just compute the scaled version, sorry, scaled vector. So yes, v, which is equal to lambda v. That is what. Okay, so that is what the exact yes it represents. Okay, and next we are just going to plot each scaled point, and let me just label each point with its scalar value. Now let we plot the 0, 0. That is what the horizon, and we also label the same 0, 0. That is horizon. Okay, and dear friends, of course you all know about this axis formatting, and we have a standard formatting for clarity and symmetric. Now let we have the title. Yes, this describes the geometric meaning, and we have an text functionalities, that is labeled the axis, and let me display the legends also. Okay, and last but not least, we have the usual one. Yes, we are just going to adjust the layout, and we want to save that exact figure, and let me display the output. Kindly observe, here we are having only one single output. Okay, only one single plot. So here the span of a single vector, that is span of a single vector, so span of a line, and here the dimensional is 1, so must pass through this horizon. So kindly just observe, dear friends, here if we just have that exact single vector, which is equal to 1, 3, the whole transpose, so it spans a single dimensional subspace, that is an infinite line through the horizon in R2. So every point of a dashed this gray line, kindly just see here, this one, yes, it just specify lambda v, which for some lambda that belongs to this real value, that is setting lambda which is equal to 0 gives the horizon, and if the lambda that is greater than 0, it extends in the direction of v, and if that exact lambda that is less than 0, it would just goes towards the opposite direction. So this subspace is the proper subspace of this R2. So it does not fill the entire plane. Points of the line, like of course like 2, 1, or here 1, 3, or minus 1.5, so in such a case, so cannot be reached by any scalar multiples of v, that is vector. Dear friends, you have only one direction. You can stretch it, shrink it, or flip it. That is what. But you can't leave the line. And here, make use of this, an important rule. A subspace must include horizon, be closed under addition or scalar multiplication. So this line satisfies both the valid subspace. And when you just think as like an data science functionalities or data scientist, yes, one features, maybe one vector direction can only represent variations along one axis. It cannot capture fully complexity of the data. Got it? Okay. Now let me just move on to the next one. Two independent vector. Okay, so two independent vector in a span of plane. And dear friends, kindly just observe here also we create a new figure with a larger size to have a, better display of 3D content. Okay, and here we are just going to add a subplot. Okay, though that is exactly a single subplot only, but we have an enables of 3D projections. Okay, and here kindly just observe we have two vectors v1 and v2, and here the first vector, of course, both the vectors are three-dimensional. Okay, so first vector v1 and second it is v2, and these vectors are linearly independent, not scalar multiples. Kindly observe. Okay, and yes, dear friends, let me just generate all. Okay, so let me just generate all linear combination. What would happen linear combination? Of course, kindly just observe we have here a line space. So it just creates a range of scalar values for coefficient. So for coefficient, of course, here we just have the linear combination as like lambda 1 v1, lambda 2 v2, and it just goes on. And that is what here we have. Of course, the range of scalar values for this coefficient, that is minus 1.5 to plus 1.5. So of 30 functionalities. Okay. So here this S1 and S2, we are just going to make use of this grid. So here it just create a grid of coefficient pair S1 and S2, where S1 it is the value of lambda 1, S2 it is the value of lambda 2. So this allows us to explore all combination of weights. And when I'm just making this, kindly just observe, dear friends, it computes the x coordinate of all points on the plane. And this one, it is the y coordinate, and here we have the z coordinate. So together these implement. Okay, so together these implement, yes, of course, we have already said, so lambda 1 v1, lambda 2 v2 for many values of lambda 1 and 2. And here, of course, we are going to plot a surface, so which represents the plane. Plane is then subspace. Okay, and here we have alpha 0.15, so which equalizes as a transparent. Okay, now let me just move on here. Kindly observe we have x, y, z. So all the things it just defines with an origin. So plotting the basis vector s from origin. And yes, the vector v1. Okay, so the vector v1 from origin, vector v2 from origin, and here we are just going to have the label functionalities for the both v1 and v2. And here's the labels the three spatial dimensions. So that is what here it is specified. And of course, you all just know about those functionalities of labels, setting label, X labels and Y labels, that is accessing labels. Okay, so labels the three spatial dimension X, Y, and Z. Okay, and now here it just describes the key concept. Yes, two independent vector that implies the 2D plane. Okay, now let me just set our camera. Okay, set our camera angle. So here observe ELEV, which is a vertical angle. So here we are just making it as a 25 degree of vertical angle. And next it is what AZIM. It is for horizontal rotation, and that is 135. So 135 degree. And of course you all know about this tight layout, show and figure it is a saving. So it is for rendering test. So let me execute and we just discuss about the output. So kindly just observe, this is what the plot we just got as our resultant, and here we have the two linearly independent vector. Okay, so v1 that is 102 and minus 1 1 2. Okay, So if we just make it towards the transpose, yes, here we just get three-dimensional functionalities, that is the component, okay. So it just span a 2D plane, that is here we just have, this is what the blue translucent surface, no? This is what the exact plane. So this plane passes through the horizon and contains every vector of this form, that is lambda 1 v1 and lambda 2 v2. The plane is a proper subset of R3, that is three-dimensional, that is point not on the plane. Kindly just observe directly along the x2 axis. Directly along the x2 axis are unreachable. Okay, so here what we just resultant it is, of course, both are in two directional. So each independent vectors adds a new direction. So two direction, that is a flat surface that is specified as like a plane. And dear friends, kindly just observe, if you are just making it with the same data science interpretation, yes, two independent features that captures a 2D structure. And data may lie on a lower dimensional surface inside a higher dimension. So this is exactly what PCA detects. And here, shortly, I just give you one thing, dear friends. If you are having as one vector, yes, it is as like a line. If you are making with the two independent vectors, of course, it is plane. And if we just go with the three independent vectors, of course, it is what the full 3D space. Now, let me just move on towards dependent vectors. Two dependent vectors that span only a line. So directly we just go towards the coding here. Kindly just observe, dear friends. So this one is create a 3D visualization. Okay. So we are just going to plot a figure, and that one we have initializing a 3D plotting axis, and here we just go with the vectors. Kindly just observe, dear friends, it is a three-dimensional component with specified as v1 and v2. And on observing the component value, kindly observe one thing. So here it is v2, which is equal to twice v1. So v2, it is 2 comma 2 comma 2, where it is 2 into multiples of 1 comma 1 comma 1. That is what v1. Yes, this clearly shows that linear dependence. And yes, let me just move on towards here. Here we are going to generate a scalar value, that is 100 values, that is from -2 to 2. Okay, and let me just compute all the scalar multiplies with this t and v1. Okay, so that is what here we are just, that is outer, which it just shows lambda v1. This is what the exact line it is specified, and this defines the entire span. Okay, so let me have the plotting the output. Okay, so that results a line through the horizon and represents the space. Okay, the represents the span also. Now here we are just going to have our plotting of vector 1, and this is for vector 2. And yes, both labeling towards this vector 1 and vector 2. And next, of course, you have already seen about this, the 3D axis. So labeling the axis as like X, Y, and Z. And here, let me just highlight the key condition. What it is? Yes, two dependent vectors span only a 1D line. Okay, so that is what, and inclusion of legend. Let me just adjust the viewing angle. Okay, and let me just find the rendering steps of tight layout on saving the figure, and let me display by execution. So here we just go with this output. So dear friends, although we have two vectors v1 and v2, okay, So is linearly dependent. Kindly just see here, both are in the same. So the first line we have 1 comma 1 comma 1, where the second vector adds no new direction. So the spans collapses from an expected 2D plane down to the 1D plane. Sorry, 1D line. So what this exactly illustrate is one thing I just want to let you know, dear. Kindly just observe. So here, if I just say the dimensional of span of the set of vectors v1 or v2 till vn, if it is in a dictionary, so it just equals to number of linearly independent vectors in a set. Okay, so number of linearly independent vector in a set. So for an independent set, the dimension of a spanned subspace equals the number of vectors. And here for dependent set, the dimension is strictly less than the number of vector. So the exact relationship is formalized by matrix rank. And here I just want to give you with an data science interpretation. Dear friends, in a data science, we have number of features. Let me just have P features. If some features are exact linear combination of other, okay, the effective dimensionality of the data is less than the P. So this is called the multicollinearity and is causes the numerically instability in regression. So here if we have if features, if it is Q features, as of course multiple of feature 1, okay. So this is what the exact multicollinearity. And even it adds new zero informations, okay, and reduces effective dimensionality. This is what we have already seen. And yes, of course, dear friends, more vector which is not equal to more dimension. So only independent vectors increases dimension. Kindly just keep it in mind, that one. Okay, now let me just move on to basis. Yes, a basis for a subspace is a set of vectors that spans the subspace, that can reach every point in it, and of course the linearly independent, that is no redundancy. Dear friends, think of a basis as a set of rulers for measuring a space. So the same point can be described using different basis set, that is different rulers. But each basis assigns a unique coordination to each point. Here, let I just give you a standard basis. So kindly just observe, dear friends. Here, the most familiar basis is a Cartesian. Of course, you all know. Or a standard basis consists of unit vector along each axis. Here, for an example, if we just have S2, which is equal to, here we just have it 1 comma 0 and 0 comma 1. So here, observe, this is one among the set 1 comma 0, okay, and 0 comma 1. So this is among one set. And here another one which we just give S3. Of course, here also it just have the standard basis of one thing. So observe, this is 1 comma 0 comma 0. Okay, 1 comma 0 comma 0. So here how we are just going to make it is as like 1 comma 0 comma 0 comma 0 1 0, and lastly it is 0 0 1. This is also another dictionary. Okay, so dear friends, kindly just observe here, this exact S2, it just defines the standard basis of R2. And here we are just having three-dimensional functionality. Yes, standard basis of R3. And each vector points along one coordinate axis. Each point one coordinate axis. How it happens? Yes, of course, kindly just observe this exact one which we just specified, yes, can also be as like E1, which is equal to 1 comma 0 comma 0. And here this is E2, which is 0 comma 1 comma 0, and here E3, which is 0 comma 0 comma 1. So each vector points along one coordinate axis. So yes, let me just provide that labels also. Okay, so here we would just have it. And this exact for loop, yes, dear friends, it loops through this two-dimensional basis vector and prints them. What it is? E1 and E2. That is what here. Okay, and yes, we are just going to have the printing for that label also, label for 3D functionalities, that is E1, E2 and E3 for this R3 combination. Okay, and one thing in important functionalities, yes, we are just going to introduce a verification of key property for this by using orthonormality. Okay, yes, let me just compute the dot product. Yes, for making it orthonormality, for verifying it, we are just going to have a dot product functionalities, that is E1 dot E2. Okay, so by using this dot product, okay, E1 dot E2, which is equal to 0, yes, confirms the vector are orthogonal. Orthogonal is in the sense perpendicular. Okay, so here let me just exactly we are going to compute vector norms also. Vector norms, of course, by using this unit vector functionalities. So how it just resembles, yes, kindly just observe unit vector of E1, which is equal to 1, and the same unit vector of E2, that is also which is equal to 1. So this confirms both vectors have unit length. Okay, so that is what here specified. Let me just observe it by executing this, and yes, see here, dear friends. So here the standard basic vector, of course, E1 and E2 are orthogonal, and the unit vector of E1, which is equal to 1. Okay, so any point here, if I just specified any point here as P1 or P2, that is transpose, which is expressed as like P1 E1 or P2 E2. So the Cartesian coordinates are literally the weights in the linear combination. And dear friends, the standard basis is so natural that we rarely think of coordinate as linear combination. But every coordinate is secretly a weighted sum of basis vector. So this perspective becomes critical when we switch to a different basis. Okay, I just give you a small summarization of this one because it is very much important. Kindly just observe, dear friends, here we have just discussed about spans and the same thing about linear independent. Yes, okay. So here, what is this independent? Of course, no vector is redundant. That is what independent. And to the same spanning, yes, that can reach any point in the space. And here we just took two vectors as like points P1 and P2 that can be written as like P1 E1 plus P2 E2. That is what the point. Okay, so this coordinates are just weights in a linear combination. But here, when we just seen towards this deep intuition, what we have when we say a point 3 comma 1, okay, actually what it means 3 into 1 comma 0 plus 1 into 0 comma 1. This is what? This is what the exactly meaning. So you are always doing this implicitly. And here, when towards this data science interpretation, kindly just observe, dear friends, whenever you just take a futures, of course, it is what the exact basis direction. And here, what the data point specify? Yes, it is one the combination of direction, combination of those direction. Okay, kindly just keep it in mind about this. Even the standard basis is so natural that we rarely think of coordinates as linear combination. But every coordinate is strictly a weighted sum of basis vector. So this perspective becomes critical when we switch to a different basis. Okay, now let me just discuss how this happens. That is, we are just going to have alternative basis, that is same space but different coordinates. Okay, let me just see it with an example. Kindly just observe. So here we are just going to create two figure. Okay, so with two panels. Left side, let me just have the standard basis, and the right side, let me have the alternative basis. Okay, so now let me introduce the definition of two different bases. So here it is what? So S1, S2 and T1, T2. Okay, so this S1, S2 defines the standard basis. So here kindly just observe, this is what array with 1, 0 and 0, 1, which is a standard. So in such a case, how this has been expressed is as like E1 which is equal to 1 comma 0 and E2 which is equal to 0 comma 1. Okay, and when coming towards this T1 and T2, yes, it is an alternative basis. Okay, so it just defines as like T1 which is equal to 3 comma 1 and T2 which is equal to minus 3 comma 1. So that is what here it is defined. And yes, these are still linear independent and of course spanning R2. Okay, yeah, two-dimensional functionalities. And yes, kindly just observe dear friends, these are our two data points of this two-dimensional. Okay, so now let me just create the two plotting. So first, let me have the standard basis under panel A. And yeah, we are selecting the left panel. Okay, and here the loop starts. Okay, loop starts over standard basis vector. Okay, and how come this happens is, yes, we are just going to draw a full axis line in both the direction. Okay, and once done, yeah, we are just going to have the basis vectors arrows also. Okay, as an arrows, and next we are just going to label that basis vector. Okay, and dear friends, kindly just observe here, we are having a plotter. Okay, so this exact plot we are just going to specify it is in the name of P, and yeah, this is what this 3 comma 1. Okay, so this is the point 1, 3 comma 1, and next, yeah, we are just going to label it using this standard coordinates. And yeah, next let me just have the second point Q, which is minus 6 and 2. Okay, so that point we are just going to draw it here. So let me plot it here. Okay, and let me label it with this kind code. Okay, now let me have this and dear friends, of course, you all know this one, the coordinate for limits and making it an equalizing. And here, yes, this is what the exact title. To make the title emphasize, coordinate is standard basis. Okay, coordinates in standard basis. And let me just move on to the panel B. So here we are just going to choose the right panel. And next, loop through this alternative basis. And yes, dears, the again thing, we have just chosen dashed lines along new basis direction. And here we are just going to draw this, that is vector T1 and T2, two vectors, and labeling them here. Okay, and this makes the exact plotting P again and labeling it as a new basis coordinate. Okay, and here I just want to surely specify one thing. Kindly just observe this exact new basis coordinate and how it happens is. So yes, let I just make this one. Previously in the standard basis, so P which is equal to, we just specified 3 comma 1. Okay, and Q we just got already minus 6 comma 2, but here in this alternative basis, okay, so this is panel B and here it is panel A. Okay, and here of course the new basis coordinate, it would be P which is equal to 1 into T1 plus 0 into T2. Okay, so this is happens. And yes, let me just plot the Q also. Yes, here 0 into T1 plus 2 into T2. So that is what happening here. Okay. So that is the exact value. It is provided in this exact vector. Okay. And once on plotting, let me just labeling it with the same and setting the title. Yes, here alternate functionalities. Okay, so once done, yeah, we are just going to highlight the coordinates, and next let me just finally render it. Okay, so once done, let me observe what would be the output. So here we just go, dears. So kindly just observe. We are having same points. Okay, same points P and Q, but we have different coordinates depending on to the basis. So here when coming towards the standard, yeah, we have P is equal to 3 comma 1. But when coming towards this alternative, kindly just observe P is equal to 1 comma 0 the transpose. That is, the point didn't change, only the description changed. Kindly just observe the exact location. And here a basis is like a coordinate system. Yes, change the axis, change the numbers. So the underlying point says the same. And dear friends, kindly just observe here the same on Q also. Dear friends, this basis here, when we just choose the point P, it is simple 1 into T1. And point Q, it is 2 into T2. That is what happened. So much simpler coordinate than in the standard basis. So the data point themselves are unchanged. Only the description here, it is 1 comma 0 transpose or 0 comma 2 transpose. That is what the difference. And this is the core insight behind dimensionality reduction. Find a basis that describes the data more compactly. And dear friends, here I just want to specify exactly, yes, this is what exactly when happens in PCA or SVD, all algorithms of selecting optimal basis vector for a specific objectives. So here, let I just give you a small summarization point. So here, of course, if you just specify basis, yes, it is what the way to describe the space. And when you come towards the coordinate, yes, this is what the weight in that basis. And last but not least, changing the basis. Yes, this is what changing the perspective itself. Okay, now let me continue on solving some coordinates numerically. That is by using that linear algebra functionalities. Okay, so where this becomes computational. Okay, so here we just go, dear friends. So kindly just observe. This is what, so verifying basis coordinate numerically. That is in the same thing. So here we have two different functionalities. So defining the alternative basis, that is 3 and 1 minus 3 and 1. Okay, so this defines the alternative basis vector. So T1 it is 3 1 and T2 it is minus 3 and 1. So these form a valid basis because they are independent and spanning. Now let me just move on to the next two standard coordinates. Okay, so P and Q. Yes, of course, it is 3 and 1. Here it is minus 6 and 2. Okay, so this defines 2 points in standard coordinates. And dear friends, next we are able to have to find the scalar a comma b in such that kindly just observe this exact point where it happens is one thing I just let you know here. So a t1 plus b t2, that is what our data point. Okay, so with this, how we are just going to make it? Yeah, we are going to rewrite the problem in the matrix formation. So we have, so kindly just observe when we just take it towards this point, we are just going to rewrite it with the matrix formation, and that exact process, it comes as T when you just make it with an product of alpha, which that gives our point. So here, what is actually T? Yes, we already have T1 and T2 as our vector, and towards this alpha, that is what A comma B, the whole transpose. Okay, with this only we are just going to construct the matrix. Okay, so yes, by using this column stack, not only with the column stack, yes, we are also going to have it with the coordinates. Okay, so let me just first of all let me just take it towards the construct the matrix by using this column stack. Okay, so here we have T1 and T2 which we are specifying it with the T matrix. So yes, let I just make it so T which is equal to 3 1 minus 3 1. So this is what our, so each column is a basis matrix. Okay, and here we have observed this difference. So NP linear algebra, we are just going to solve it. Okay, so solving the system, what we just get, yes, it just returns the coordinate of P in the new basis. So how this happens? Yes, if we just have the coordinates of this one, it would be written like this. And yeah, does the same for point Q also. Yes, here we have towards the Q values. Okay. Yes, dears. Now let me just print the basis matrix. That is what here it is there. And not only that, we have the original point, and it is also going to display its coordinate in the basis T. Okay, and dear friends, kindly just observe here, we are just going to reconstruct the point using the new coordinates and what it is. So observe here what it happens. So this is AT1 and this is BT2. Okay, so confirming the correctness, I just want to make it repeating same for the coordinate Q also. Okay, and let me just verify the reconstructions, and here once on execution, let me have this. So observe dear friends, here on changing the basis, let me solve the linear system. So we are changing the linear system, and here how it happens. So on making this particular line, so on this line, linear algebra, to solve this matrix, to solve this system, okay, so we use the exact particular one. So kindly just see here, this one, T alpha which is equal to P. Now how this has been computed is alpha which is equal to 3 transpose P. Okay, and yes, coordinates are obtained by inverting the basis transformation. And yeah, kindly make the same thing for this Q also. And dear friends, this one, it is very much useful where basis vector form a matrix T. Okay, and any point in the space that can be written as like see, even though you can just have it like alpha T alpha which is equal to P. Okay, you can also have P is equal to T alpha. Yes, and you can just solve what is this alpha itself. Okay, and yes, by using that you can just solve alpha which is equal to 3 transpose of P. So the solution is unique because T is the basis, that is the independent. Okay, yes, if the vector were dependent, T would be singular. If the vector is dependent, T would be singular, and here this exact NP dot this linear algebra, so solving this system, yes, would fail, and here no unique coordinate would exist. And dear friends, when coming towards this data science interpretation, yes, this operation is what exactly this PCA, that is PCA projection, that is projecting data into new bases. So dimensionality reduction, that is what happening. And not only here, yes, SVD transformation, that is for coordinate change, and feature transformation for new representation, that is what happening, dears. Okay, now let me just move on to see why independence matter for a basis. Actually, this is based on multiple representation issues. Multiple representations. It is very important conceptual closure, dears. Okay, now let me just make use of this. Dear friends, a set can span a space but still fail to be a basis. Okay, now let me just, by using this one, okay, so let me just start to create an vectors. Okay, so here kindly just observe, we are going to define a vector u1 in a form of array as a 0 comma 1, and vector v2, yes, with the components 0 and 2, and vector 3, yes, it is having the component of 1 comma 0. And dear friends, one thing kindly just observe here, when on just deeply thinking about this u1 and u2, yeah, here you can notice one thing. So u2, which is equal to twice u1, yes, u2 it is 0 comma 2, and u1 it is 0 comma 1, twice the exact number. Okay, so these two are linearly dependent. And when coming towards this u3, yeah, it defines the third vector u3, which adds a new direction. Okay, so now let me just check with the stat vector. Okay, column stacks we are just going to do, and vector into a matrix formation. And here this exact line, it just displays the matrix what it has with an title. And yeah, next we are just going to compute what is our rank. Okay, and here of course when on just specifying, we are able to compute, yes, the rank it would be 2. Now next let me just move on to the number of vectors here. Of course, yes, we have 3 vectors. It is already known, that is u1, u2, u1, 3. And dear friends, here with this, let me just have the particular functionalities here, making a representation of 1, representation 2, representation 3, what it just actually gives. So with the point P, 3 comma 1, we are going to represent 1. Okay, so the exact representation 1, what it happens, kindly just observe one thing, dears. So here it shows us like P, which is equal to 1 u1 plus 0 u2 plus 3 u3. This is what happening. Okay, so this is what 3 into u3. Okay, when on representing this R3, so here it is R1 and here it is R2. Okay, so this R2, what it happens, it is, yes, exactly 0 U1 plus 0.5 U2 and plus 3 U3. Okay, and last but not least, we are just going to have our representation 3, where P, which is equal to minus 1 U1 plus 1 u2 and plus 3 u3. Okay, and now let me just print our points. Okay, so with this, let me just print our points, and here once on printing the point, it just goes to show the first coefficient, second coefficient and third coefficient. And critical observation is, yes, the same point and different coordination. Same point and different coordination. And last but not least, here whether the coordinates are unique, not unique, like that. Okay, so let I just execute and see what is the output. Yes, dear friends, kindly just observe here. See, all the given points are same, but the different in coordinates. Okay, so this ambiguity is why dependent sets cannot be bases. The matrix formed from this U, yes, of course, has a rank 2, but the coordinate vectors are 3. So conforming dependency, the critical consequence point P, which is equal to 3 comma 1 transpose. Okay, so here can be described by multiple different coordinate triples. Okay, for the representation 1, yes, kindly just observe here it is what the point, and for the representation 2, the exact the point, and this is for the representation 3. And dear friends, here the coordinates are not unique, which makes U useless as a measurement system. So basis must all assign exactly one coordinate to each point, and only linear independence guarantees this uniqueness. And yes, observing towards this output, what happens? Kindly just see here. the basis which is equal to this spanning and with an independence. We have multiple coordinate representation but no consistent measurement system. And dear friends, yes, if features are dependent, multiple parameter solutions exist, model becomes unstable, coefficients lose meanings. This is what, yes, multicollinearity is a problem. And regularization or of course this PCA techniques would be used. So let I just give a small finery picture here. Kindly just one thing observe, dear friends. If you are having this linear combination, yes, kindly just build vector. Okay, and of course, if it is an independency, kindly just remove the redundancy. And the third one, yes, for a span, kindly define the space. And last but not least, for a basis, yes, perfect representation system is must. Okay, so all these things. So yes, that is what has been given here in this important point. How about this PCA? How about this SVD or ICA or linear discriminant analysis, Fourier transformation? Okay, what it actually does and what is the exact basis perspective of this functionality I have just given here. Okay, so this is the exact summarization of this whole the things which we have done above, but not here we are not stopping. Of course, we are just going to have a comprehensive of whole the things what we have just seen above. Yes, kindly just see here, this is the full combination of vector dependency, sorry, vector set, dependency, span and basis. Okay, and kindly just observe, we are going to define a vector A which just has a point along with the x1 axis. Okay, and here we are defining a point B with the x2 axis, and last but not least here we are having a point C. And observe towards this C, dear friends, here it is added towards that where C is equal to A plus B. Okay, C is equal to A plus B, which defines that is the summation of. So the summation of that is C is dependent on A and B vector. So this is immediately implies this particular, yeah, the resultant of C always dependent on to the result of A and B. Okay, so let me just have a column stack. Okay, here let me form a matrix with the column A comma B comma C. And once done, let me just compute the rank. And yes, of course, here the number of independent vector is noted, that is computed. Okay, and by using this particular print function, yes, it just prints the vector and explicitly shows the dependency. And yeah, this one, it is not but not least, yes, this displays the matrix. And we are just going to have the vectors. Okay, number of rank, number of vectors, and yes, if it is dependence on whether it is lesser or higher. Okay, in such a case, we are just going to conclude, yes, the set is whether it is linearly dependent or not. Okay, and now let me just we are just going to introduce some testing smaller subset. Okay, so in that subset, kindly just observe, we are just going to have that subset by making in a loop through all pairs of vectors. So here we have two things, one is M and the next one it is R. So now N, of course, it is what the column stack, that is the pair, and we are just going to calculate the rank with the variable R. Okay, so here for each pair, building a matrix and computing the rank, that is what simultaneously it is going to have, that is within this loop. Okay, and now once for all, we are just going to print what is the rank and about towards the subspace and towards the whether it is dependent or not. And not only that, we are also going to have the basis evaluation. Okay, so here the basis evaluation is also done, and here once done, the value of A and B is a valid basis or not. That is what the conclusion we are just going to have. And another valid basis also, yes, kindly just to see here, different vectors, okay. So different vectors with the same space, that is also we have to note it onto that. Whereas important distinction is that is spanning alone is not enough. We also must need also be known to that of independent. Okay, so that is what here it is very much important. And let me just execute it and kindly check with the output. So see here, dear friends, all the things. So this is how we have the vector set. Okay, so vector set A comma B comma C, where C which is equal to A plus B. And next, what this shows. Okay, so yes, clearly I just let you know the first point about the vector set. So here we have a set of A, B, C, where in such case we just resultant with C is equal to A plus B. Okay, now the second one, yes, it is all about how this happens. So A plus B minus C, which is equal to 0. So here on towards this linear dependency, it is said that non-trivial components. So it is a dependent. And yes, next let me just move on to the third one. Yes, it is all about span. So kindly just observe here, dear friends. So all vectors lies in x1 and x2 plane. So here what would be the dimension? Yes, it is the dimension is 2. And when coming towards the basis, dear friends, kindly just observe here we have a valid basis of, yes, A comma B and to the same of A comma C. But here we are having an invalid. Of course, this is an invalid. ABC is an invalid because it is not independent. Okay, and yes, all to the last. Yes, dear friends, adding more vector does not increase dimension unless they are independent. And towards the data science interpretation, I want to specify, dear friends, even though if you just have extra features, it is not equivalent. Yes, it is not going to give you a more information. So only dependent features matter. Okay, so yes, let me just move on to how this happens towards being implemented in an application. Okay, till now we have discussed the foundation of this vector set, linear combination, independent, span and basis. Okay, so let me just implement in three widely used data science techniques. Yes, Pearson correlation, cosine similarities, time series filtering, and last the third one k-means clustering. Dear friends, this one, each one built entirely from the vector operations. But in this session, we are just going to discuss only on towards correlation and cosine similarities. Yes, the dot product as a similarity measures with normalization. Okay, let me just discuss here, and I'm just going to make a demonstration about the three important correlation behaviors. Yes, positive correlations, negative correlation, and zero linear correlation. Okay, now let me just begin with some data points. So here it is specified as like a 200. So we begin by defining the number of data points as 200. And yeah, a random seed, kindly just observe, a random seed is set to ensure reproducibility. And this guarantee the same random values each time the code executes. Okay, the code runs. And here for this positive correlation, yeah, we are just going to generate a data set with positive correlation, and the variable this y positive depends on the x positive scaled by 0.8. and with added with some noise. Okay, so that is what here, and this creates a clear upward trend because it is scaled up and also added up. Okay, but when coming towards this negative correlation, kindly just observe, dear friends, here whenever you are x, that is x negative increases, we can easily observe that is a trend to be decreased in y negative due to the negative coefficient. Okay, and next one, it is all about that is the zero linear correlation. See, this data set has no strong linear correlation, but it has a non-linear structure. Okay, so the relationship here, it can be as like quadratic. So this is important because Pearson correlation only measures linear relationship. Okay, now let me just have a plotting. Okay, so we can create a figure with three subplot to visualize all data sets side by side. And yeah, we are just going to organize the data set into a list, pairing each data sets with a descriptive title. Okay, and next here we are just going to have the looping. So we iterate over each subplot and corresponding data simultaneously. Okay, so for each data set, we are just going to compute the Pearson correlation coefficient by using the NumPy. Okay, so the result is extracted from the correlation matrix, and we are just going to plot the data in a scatter plot. Okay, and each point represents a pair of value with x and y. And dear friends, here let me just we label each pair, each plot with its title and computed correlation value, and this makes interpretations immediately. And here also we are just going to have a label. Okay, the axis for clarity. And last one, yes, of course, we are just going to adjust our layout and saving the figure, and let me just display it. And kindly just observe, yes, finally we print the correlation values numerically for all the exact three data sets. Okay, and kindly just observe the exact data points here, dear friends. So when on just making this one, so this positive correlation, yes, similar towards 0.081, of course, approximately a strong positive relationship. As x increases, the value of y tends to increase proportionally. And when coming towards this negative correlation, kindly just see here, this exact probability, it just results to minus 0.66. So here, a moderately strong negative relationship, as here, kindly just see here, whenever there is an increase in x's, y tends to decrease. And last but not least, the right last one. So kindly just see here the exact Pearson correlations. It is just a probability of 0.28. That is a modest linear correlations exist. Because x square has a slightly, x this one, and x square has a slightly positive tilt when x is not perfectly symmetric. So x, the dominant relationship y is equal to x square plus epsilon. That is, it is clearly non-linear. And here Pearson correlation captures only the linear component. So this is critical limitations. A moderate P can mask a much stronger non-linear relationship. And dear friends, always visualize your data before trusting a single correlation number. As combining quartet and the data as dozens or classic examples where very different data sets produce identical correlation coefficients. Okay, let's build the correlation coefficient from scratch using only this NumPy functionalities. Yes, by using np dot and yeah, we are just going to have np dot linear algebra with the norms. Okay, to demonstrate that it really is just three dot products. Okay, yes, Kindly just let me start with this coding. Kindly just see here, dear friends, we begin by creating copies of the input vector. Okay, so we are just going to have the copy of input vector x positive and y positive. Okay, so that is what here, and this ensures that any modification we make do not alter the original data. So that is what here we just made it with a copy. And next, here we are just going to, in the step 1, we are just going to perform mean centering. We subtract the average value of each vector from every element. So this removes any constant offset, allowing us to focus purely on how the variables vary really to their mean. And next, it is going to the step 2. That is, here it is already given the command, yes, dot product of mean centered variable. And dear friends, we are just going to compute this dot product between the mean centered variables. That is, this forms the numerator of the Pearson correlation, and it measures how much the two variables move together. And next one, the step 3, product of norms, that is denominator. Yes, we compute the magnitude or norm of each centered vector. So when they multiple these norms together, this becomes the denominator. So which normalize the results to remove scale effective. And next here, this is what the Pearson correlation. Yes, we divide the numerator by the denominator. So this gives the Pearson correlation coefficient, denoted as RHO. So the result is guaranteed to lie between -1 and 1. And to verify manually, okay, to verify manually implement, we compute the correlation using NumPy built-in functions. Okay, so we extract the correlation value from the resulting matrix. Now, let me just print it. Yes, we are just going to print with a small header to clearly label the output section. And yes, here these two lines, it is just going to print the mean value of x and y. So conforming the center step. And yes, the next one, we are just going to print the dot product of the centered vector, which represents their dot variation. And yes, dear friends, here this one, we just have the lines shows the norms of each centered vector representing their individual variability. Okay, and next one here, it just shows the denominator, which is the product of the two norms. And next one, manually. So this prints the manually computed Pearson correlations with high precision. Okay, and this one, the NumPy computed correlation for the comparison. Okay, so finally we compute the display, the difference between the two results. And yeah, let me just execute here. So kindly just observe, dear friends, what is the exact mean value, and towards the mean of x, mean of y. Okay, so here, as highlighted already, okay, I just want to let you know one thing, dears. Hold the exact correlation. It is computation, it is reduced towards here. Kindly just see here, x mean transpose y mean, and divided by, yes, of course, x mean under unit vector and y mean unit vector. Okay, so which mean, yes, this correlation, that is normalized dot product, okay, and geometrically cosine of the angle between vector, that is after centering. So here this numerator is large and positive, when both, kindly just to see here, when both variables tend to deviate from their means in the same direction, the denominator normalize away the unit and magnitudes, guaranteeing that -1, which is less than or equal to p, which is less than or equal to 1. Okay, now next, let me just move on to the cosine similarity. Dear friends, the cosine similarity uses the same formula but without the mean centering. One and only things, kindly just observe. So here, this cos of theta x and y, which is equal to, yes, here x transpose y and unit vector of x dot product y, unit vector of y. So that is what. So here, yes, the cosine similarities uses the same formula but without mean centering. And when the data happens to be mean centered or equivalently when the mean is 0, and Pearson correlations and coefficient similarities are identical. Otherwise, they can diverge. Okay. Yes. Now let me just discuss it with an coding here. So kindly just observe, dear friends. Here we begin with defining two vectors A and B. Okay, so notice that both vectors follow the same pattern, but B is shifted upward by 100 units. 0, it is 100. 1, it is 101. 2, 102. 3, it is 103. Okay, so this offset will be important when comparing correlation and cosine similarities. Now the next one, we compute the Pearson correlation, okay, between A and B. So this method automatically subtract the mean from each vector before computing similarities. Okay, as a result, it focuses only on how the variable change relative to their averages. And next, here we have the one which we compute the cosine similarity. So this is simple, the dot product divided by the product of the vector norm. Okay, unlike correlations, this method does not remove the mean. So absolute value influences the result. Kindly just think over this. Okay, absolute value influences the result. And here we have the one. Okay, so we now explicitly mean center both vector, but this step transforms the data so that both vector are centered around 0. Okay, around 0. And next, of course, we compute cosine similarities again, but this time using the mean centered vector. So this makes cosine similarity mathematically equivalent to the Pearson correlation. Okay, now let me just print the original vector to confirm their values, and this displays the Pearson correlation value. Okay, so this value is exactly 1.0, indicating a perfect linear relationship. And yes, here we have the cosine similarities. We are just going to, that is without mean centering. Okay, and next display the cosine similarities after mean centering. And next we are just going with mean centered. So the transformed vector. Okay, so let me just have the output here. Kindly just verify. So observe, dear friends, here towards this value. Yes, this one. So this is what the cosine similarities. And when you just combine towards the Pearson correlation, cosine similarity of mean centered. That is what cosine similarity, and cosine similarity with mean center, it is what Pearson. Okay, and dear friends, Pearson correlation ignores offset, that is deducts shared trends. And here cosine similarities includes offset where sensitive to absolute position. And till now we are just speaking on about all these time mean center, mean center. See, mean centering aligns both method, they become identical. And if you would just ask when to use this Pearson or when to use this cosine similarities. So for them, kindly just have a note, Pearson correlations when you care about relative changes. That is, do the variable move together, okay? So standard for most statistical analysis. And towards this cosine similarities, yes, when the absolute value matter, not just their deviations. these are all very much common in natural language processing. That is mainly on this document similarities via this TF-IDF or embedding. So when a vector of word frequency should not be artificially centered, na? So that time this cosine similarities is very much important. Okay. So yes, next let me just move on to have. See, we are just going to have all the one in a single combined practice. Okay, so we often compute correlation between all pairs of variables simultaneously. So the result is a correlation matrix of this real values. Okay. Yeah, let me just begin with an 300 data points and of course random seed 42. Okay, so we begin by generating a latent variable z. Okay, so this latent factor which we just specify hidden factor will influence multiple variables creating correlations. Okay, and of course this is what we construct of 5 variables. We construct 5 variables v1, v2, v3, v4, v5. So this exact 5 variables, kindly just observe this first 3 depends on this z. The first 3 depends on to this z correlated, and of course this fourth one it is purely noise, that is uncorrelated, and the fifth variable, this is a non-linear where weak linear correlations happens. Okay, so we assign all these names to each variable for labeling the matrix. Now, let me just compute the correlation matrix and kindly just observe here. So, setting here row variable is equal to false, which means each column is treated as a variable. Now, let me initialize a figure for visualizing the matrix, and we display the matrix as a, of course, in a heat map. And here a color bar actually is added to interpret the values visually. And here we have just defined the tick position for both the axis, and we label rows and columns with variable names also. And here we have a loop. So kindly just observe, we loop over every in the matrices. Okay, so every cell in the matrices, and here we have a text column. Okay, so that each cell is annotated with its numerical correlation values. Okay, and dear friends, kindly just observe, we just set our title, and we finally displays the visualization. So let I just execute and observe the correlation. So here we have the exact correlation functionalities. Dear friends, the correlation matrix summarizes all pairs or pairwise linear relationship in one structure, but it cannot detect nonlinear pattern, or it scales poorly for large data set. Okay, so now from this correlation output, kindly just see here, the correlation matrix reveals the structures we designed here. The vector v1 and v2 are positively correlated, that is 0.75, because both load on the same latent factor z. And here this v3, actually it is negatively correlated with v1 and v2. Okay, because it loads negatively on z. And here this V4 is nearly uncorrelated with everything, that is less than 0.07, because it is pure independent noise. And next, last but not least, kindly just observe this V5, it just shows that Z square, that is what is this V3 square, that is what here it is specifying. Okay, so V3 square plus some error, so has nonlinear dependency on Z, but only a weak linear correlations with V1, V2, and here observe the diagonal is always 1. Yes, each variable is perfectly correlated with itself, and matrix is symmetric. So yes, as per the diagram, yes, Ri and J, which is equal to Rij. A property we will see again when we just discuss about transpose properties. Okay, and kindly just observe, dear friends, computing this full P into P correlations we have. As I have already said, yes, this is used in very large data set. Of course, where it would be, yes, here it would be big O of n dot P the square. So which becomes expense for wide data sets. So yes, dear friends, so here we have demonstrated the abstract vector operations for the previous vector set, linear combination, independent span and basis. Directly on only the one particular concept, that is Pearson correlations and cosine similarities. So here the Pearson correlation is the dot product of mean centered variable. So yes, as I have already said, mean of x transpose divided by unit vector of x mean centered and unit vector of y mean centered. And when coming towards cosine similarities, yes, uses the same formula but without mean centering. So the choice between correlation and cosine similarities depends on whether absolute or relative values matter. Okay, so here it is as like yeah, x transpose y divided x y. So this is how we just end up with this session, dears. A linear combination to basis establishes how data can be represented efficiently and without redundancy. So these concepts directly underpin real world techniques such as correlations and cosine similarities, which quantify relationship between variables and vectors. And yes, dear friends, in the context of generative AI, these ideas are not just theoretical. They form the backbone of how modes interpret similarities, structure embedding, and learn meaningful representation of data. So mastering these fundamentals provides a strong conceptual framework for understanding more advanced system, from embedding to neural network and beyond. So dear friends, if this session helped you build a strong foundation in vector sets and linear combination, independence, span and basis, so kindly just like this video, share it with someone starting their data science or generative AI journey, and subscribe to Demystify with Ajay for more such real world discussion. And yes, dear friends, see you in the next session. Thank you. Happy learning.